Okay, so a PowerPoint for section 3.7 would be kind of pointless. Therefore, we're going to go through the notes as they are on the website, and I'll just talk my way through them. First of all, let's look at some guidelines for solving applied, minimum, and maximum problems. Basically, applied means we're going to look at word problems. Everybody wants to know, how does math relate to my life? Word problems are how they relate. So here we go. First, we want to identify all given quantities and all quantities to be determined. If possible or reasonable, make a sketch. It's not always reasonable. Number 2, write a preliminary equation for the quantity that is to be maximized or minimized. Look for keywords like find the maximum area or find the minimum volume. It'll tell you what it is that your primary equation should be. Reduce this primary equation to one having a single independent variable. For now, in Calculus 1, we work with one variable at a time. When you get to Calculus 3, you work with multivariable derivatives and integrals. But for now, we must have a single independent variable. This may involve the use of secondary equations relating the independent variables of the primary equation. Always, number 4, determine the feasible domain of the primary equation. Make sure you know that you're not going to end up with negative heights, or you can't have a height that's 30 feet inside of a building that's only 20 feet tall. Things like that. Determine the values for which the stated problem makes sense. Number 5, determine the desired maximum or minimum values by the calculus techniques of Chapter 3. This means find derivative, set it equal to 0, find where it doesn't exist. We're looking for critical numbers. Anytime we're talking about maximum or minimum or increasing and decreasing, we're looking for critical numbers of the function. Our first example is one that we would never try to create a sketch of. Find two positive numbers such that the product is 185 and the sum is a minimum. Now, where I see sum is a minimum, I know that sum means add. And I want to add these two positive numbers to get a minimum value. We're going to put s equals x plus y and call that our objective, preliminary, or primary equation. We know that the product is 185, so x times y equals 185. And we know that x and y are positive, so we've determined our domain. Now, my objective function, s equals x plus y, has two variables. That's not okay. We can't take the derivative of something with two variables. So we go back to our secondary equation. Our secondary equation is the product. X times y equals 185. In green, we see on the right, we see that if x times y equals 185, then y is equal to 185 over x. We could substitute this into our primary equation, the s equation, to eliminate our y variable. So now instead of s equals x plus y, we have s equals x plus 185 divided by x. And for purposes of derivatives, it might be easier to rewrite that as x plus 185 multiplied by x to the negative 1. Now, we want to find a minimum. That tells us we got to find the derivative. S prime, the derivative of s, is 1 minus 185 x to the negative 2. And I rewrite that now with a positive exponent as 1 minus 185 over x squared. Now, a minimum occurs where the derivative is equal to 0. If I solve where the derivative is equal to 0, then x squared is equal to 185, or x is equal to the square root of 185. Remember, we're looking at positive values only, so I only take the positive square root. If x is the square root of 185, and x times y equals 185, I know that y must also be the square root of 185. I'm not going to find the decimal for that. I don't care what the decimal for that is. What we care about is the exact answer. So we'll leave it in root form, square root of 185. Now, how do I know if this is a minimum? Because that's what we want. We want the sum to be a minimum. And we have a couple of different ways of doing this. I chose in red to use the second derivative test. The second derivative of s is going to be positive 2 times 185x to the negative 3. Or 370 over x to the third. When I put in the square root of 185, I know that the square root of 185 to the third power, whatever number that happens to be, it's positive. 370 over a positive number is positive. If my second derivative is positive, my graph is concave up. If my graph is concave up, then I know that I must have a minimum. This gives us the minimum answer we need. Moving on, example 2. This one, a sketch is more reasonable. Find the length and width of a rectangle that has a perimeter of 80 meters and a maximum area. Maximum area tells me I'm looking for an area formula. So in blue, I have area of a rectangle equals length times width. In this case, a sketch is helpful. In black, I've sketched a rectangle. Not a perfect rectangle, but work with it. Length L, width W, and I know the perimeter of any rectangle is 2 times the length plus 2 times the width. If you need to, get a formula sheet that has all these different geometric formulas on them. All right, get some formulas down if you don't have them memorized. So my perimeter is 80 meters. So 80 is equal to 2 times L plus 2 times W. This is our secondary equation. This is an equation that relates the two variables with a constant. Whereas our area equation, our primary equation, A equals L times W, has an area that we're trying to maximize. So we don't have an actual constant value for our area. In order to simplify our area down to one variable, we'll take our perimeter equation. I'm going to divide everything by 2 in order to get 40 equals L plus W. And then I chose to solve for L, but you could have solved for W instead. L equals 40 minus W. And I use this in my blue area formula and substitute. A equals LW becomes A equals 40 minus W in parentheses times W, which is 40W minus W squared. It's easier to use a distribution here rather than having to use a product rule for the derivative. Now I find the derivative, The derivative is 40 minus 2W. When I set it equal to 0, I find that W equals 20. If W equals 20, then from my formula, the length equals 20 as well. And I can check this. I can make sure this is a maximum. Notice that my second derivative of A is minus 2. Minus 2 is always negative. Always negative means it's always concave down. If I'm always concave down, I will have a maximum second derivative test. Just so you know, if you want a rectangle with maximum area, it will always be a square. So that's one of our little cheaters tests that we can use. Number 3, you have a problem just like this on your homework in WebAssign. And it's very possible that it's this exact problem. So let's take a look. Find the point on the graph of the function f of x equals x minus 1 all squared that is closest to the point negative 5, 3. So I have this function, and I want to find a distance, right? If it's closest, I'm looking at distance. And a close is a minimum distance. So I need to know the distance formula between 2 points. I need to know that closest is minimized. And I need this point negative 5, 3. Let's see what we have. When I substitute my values, keep in mind that any generic point is x, y. Well, in this case, we know exactly what y is. Y is x minus 1 all squared. It's given to us by the function. So in my blue distance formula at the top on the left, I have d equals minus 5 minus x in parentheses all squared plus 3 minus x minus 1 all squared and then squared. All right? Distance, I subtract the x's, subtract the y's, square those individually, add, and then take the square root. Now, that is an ugly looking radicand. The radicand is the thing underneath the radical. So I multiply it all out. I multiply out my x minus 1 squared, and then I do 3, subtract that, and then I square that answer. I multiply out my minus 5 minus x all squared, and then I combine like terms to end up with d equals the square root of x to the 4th minus 4x cubed plus x squared plus 18x plus 29. When we find the derivative, remember the radical is the same as the 1/2 power. I'm using the chain rule. I'll bring that 1/2 in front, leave the inside alone, raise it to the power of negative 1/2, and then multiply by the derivative of the inside. So I'm going to take the derivative of the polynomial, which is 4x cubed minus 12x squared plus 2x plus 18. When I rewrite this with the negative 1/2 power taken to the denominator, and then I divide everything by 2, I'll end up with d prime equals 2x cubed minus 6x squared plus x plus 9 over the square root of x to the fourth minus 4x cubed plus x squared plus 18x plus 29. I'm so glad this is written down for you. Now, in order to find a critical number, I need to set this derivative equal to 0. And already I'm thinking, I don't want to. But when I set the derivative equal to 0 for a rational expression, I really only have to pay attention to where the numerator is 0. Now, setting the numerator equals to 0 is pretty straightforward, excuse me. It's a cubic polynomial. We can use techniques from pre-calculus we talked about in section 2.6 if you need to review that. And we find that x equals -1 is the only real 0 for this particular function. The other two roots are complex. When x is equal to -1, I go back to my original function to find my y value is 4. So I know the point -1, 4 on the graph of f of x is the closest to the point -5, 3. Now, if I wanted to test and make sure it was a minimum, I don't want to take that second derivative. That's horrible and not fun to evaluate. So it's about at this point that I say, trust your algebra. You probably did it right. Next example. On a given day, the flow rate F in cars per hour on a congested roadway is F equals V divided by 22 plus 0.02 V squared, where V is the speed of the traffic in miles per hour. Now, if you need to, go back and read it again. Figure out what all your variables stand for. The question is the important part. In any word problem, skip down to the question, figure out what it is that you're going to be dealing with. What speed, so find V, will maximize the flow rate, so maximize F on the road. So I want to find where f prime is equal to 0. Maximize the flow rate. Set the derivative of f equal to 0 and see what my v value is. So that's exactly what I do. I use the quotient rule and I find denominator is 22 plus 0.02 v squared multiplied by the derivative of the numerator minus the numerator multiplied by the derivative of the denominator all over the denominator squared. And then I simplify and I end up with 22 minus 0.02 v squared, all divided by 22 plus 0.02 v squared, all squared. Now these look very similar and you're extremely tempted to cancel, but keep in mind, they have to be identical. If the numerator has subtraction, denominator has addition, we cannot simplify this at all. The great news is, just like in our distance derivative previously, if I want to set a rational expression to 0, I want to set the derivative equal to 0, I really only have to focus on the numerator. Set the numerator equal to 0. The rational expression will be undefined when the denominator is 0, and in this case it doesn't happen, so we don't have to worry about it. So the numerator is equal to 0, 22 minus 0.02 v squared. Add 0.02 v squared to both sides. Divide by 0.02. And I get 1100 equals v squared. Take the square root of v, and you'll get the square root of 1100. Our velocity is the speed of traffic. I know sometimes in El Paso it feels like it's going backwards, but our velocity never actually is a negative, so this is positive square root of 1100. And if you ever tell your passenger that you're driving at the square root of 1100 miles per hour, they'll probably ask you to pull over so they can call a cab. So let's simplify that in a real life problem like that. Square root of 1100, let's call that 33 miles per hour. 33 miles per hour is the velocity that will maximize the flow rate on the road. So that's important to notice that it's not always the speed limit that makes the flow rate go better. In red, notice that f prime is never undefined. It's never undefined because our denominator can never be 0. If v is 0, then we'll have a denominator of 22 all squared in our derivative. So we're good there. So how do we know this is a maximum and not a minimum? The first way we know is because it comes from a textbook and they're not going to give you a problem like that. But the way we really know through calculus is we do a first derivative test. We could do a second derivative test if you feel like it, but I'm going to use a first derivative test. Put square root of 1100, which we know is approximately 33 miles per hour, on your number line. Pick any number to the left of it. I chose 20. Pick any number to the right of it. I chose 50. Evaluate it in your derivative. When it's positive, it's increasing. When it's negative, it's decreasing. And this shows us that we have a maximum at our 33 miles per hour. Always a good idea to test your work. And unless that makes you question your abilities, then don't. All right. Example 5. A rectangle is bounded by the x and y axes of the graph of y equals 6 minus x all over 2. I took this problem directly from WebAssign. You have this exact question as a homework problem. I don't want to have to answer any questions on WebAssign since I'm giving you the answer here. What length and width should the rectangle have so that its area is a maximum? All right, so I'm looking at the area of a rectangle. That's my primary equation, a equals xy. I know what my y value is. Y is equal to 6 minus x all over 2. So I can substitute. A equals x multiplied by 6 minus x all over 2. And if I simplify that, I end up with 3x minus 1/2 x squared. Moving on to the blue writing. I know my maximum occurs when the derivative is 0. So I find the derivative. A prime equals 3 minus 1/2 times 2x, which is the same as a prime equals 3 minus x. I know that that derivative is equal to 0 when x is equal to 3. So the rectangle length is 3 units, and the width is y equals 6 minus 3 over 2. 6 minus 3 over 2 is 3 over 2, or 3/2 units. Now, notice that in our figure, that's exactly what the rectangle looks like. Don't count on that happening in general. It just so happens that this one gave you the answer in the picture. But that is not something you can count on WebAssign doing for you all the time. All right, moving on. Example 6. A solid is formed by adjoining 2 hemispheres to the end of a right circular cylinder. Picture a Pepsi can with a tennis ball cut in half, and each half put at the end of the can. The total volume of the solid is 14 cubic centimeters. Volume, cubic units, so we know there's 3 measurements here. Find the radius of the cylinder that produces the minimum surface area. So I know I'm looking at a right circular cylinder. If I don't have those formulas memorized for volume and surface area, I'll need to go look those up. In this case, my volume of the cylinder is 4/3 pi r cubed. Excuse me, that's so not true. That's my volume of a sphere, 4/3 pi r cubed. And the volume of the cylinder is pi r squared h. And I know this adds up to 14. All right, so it's in 2 parts. The 2 hemispheres have the volume that make up 1 sphere. So that's my 4/3 pi r cubed. And then the volume of the cylinder part is pi r squared h. Our surface area, the surface area of a sphere is 4 pi r squared. And the surface area of a cylinder, without the ends because they're covered, is 2 pi rh. Now, I want to minimize surface area. I have a variable r, I have a variable h. I need to solve for h. H looks like the easiest to eliminate. In the volume formula, I'm going to solve for h in order to substitute that into the surface area formula. So in blue, you can see where I've solved for h using the volume formula. Over on the left, underneath the diagram, I've taken the surface area equation and I have substituted for h, and I've canceled out all relevant variables. Distribute your surface area is 4 pi r squared plus 28 over r minus 8/3 pi r squared. But if I have 4 pi r squared minus 8/3 pi r squared, how about we simplify that? And the surface area is 4/3 pi r squared plus 28 over r. Now we need to find the derivative. The derivative of the surface area in green in the middle is 8 pi thirds r minus 28 over r squared. I want to set my surface area equal to 0. I know a radius of 0 makes my surface area, the derivative of the surface area undefined, but we're not going to have a radius of 0. We'd have nothing. All right, so we don't have to worry about that. Set the surface area equal to 0. I'm going to add 28 over r squared to both sides. I'm going to cross multiply. Anytime you want to solve a proportion, you cross multiply. And I have 84 equals 8 pi r cubed. It looks like one of the legs of my pi is missing. Get r cubed by itself, 84 over 8 pi. Take the cube root of both sides. R equals the cube root of 84 divided by 8 pi. When you put this in your calculator, you might need parentheses around the 8 pi to come out with the correct answer of 1.495 centimeters. So a cylinder of 1.495 centimeter radius with a total volume of 14 cubic centimeters. Hemispheres on the end, this is going to have minimum surface area. Why might we care? Maybe they're making a canister that holds tennis balls or holds golf balls, and they want minimum surface area because they want minimum cost in the production of the materials, but it has to hold a certain amount. These things come into play in a variety of areas of commerce. All right, a wooden beam. A wooden beam has a rectangular cross-section of height h and width w. The strength S of the beam is directly proportional to the width and the square of the height by S equals kWh squared, where K is the proportionality constant. What are the dimensions of the strongest beam that can be cut from a round log of diameter 20 inches? All right. If you need to go back and read that again, you should go back and read that again. What I get from the diagram is a nice little Pythagorean theorem here. I know that my triangle with a W, H, and D diameter, right? A diameter of 20 inches, so D is 20. I have W squared plus H squared equals 20 squared. I can rewrite that, solving for H squared, as H squared equals 400 minus W squared. Now, why did I want to solve for H squared? Look at our formula. We want to get the strongest beam. So the strength is S. I want it strongest, so I want a maximum strength. Being able to interpret the words, very important. A maximum strength, the S formula is going to be my primary equation. Because I want it maximum, I want to find the derivative. As I'm looking at S, I see that K is a constant, no big deal. W is a variable, H squared, where H is a variable. H squared is easy to substitute for. That's exactly what I do in blue. S equals KWH squared becomes KW times 400 minus W squared. And I can multiply that out to get 400 KW minus KW to the third. Find the derivative to find the maximum. Set it equal to 0. I have 0 equals 400K minus 3KW squared. Keep in mind, K is a constant. When I solve for W, I'm going to add 3KW squared to both sides. Divide both sides by 3K. The K's cancel out. W will equal the square root of 400 divided by 3. Now, square root of 400, that's 20. Square root of 3, I don't know, let's just call it square root of 3. I could rationalize and call this 20 square root of 3 over 3. If I wanted to actually tell a logger the size that they needed, I would say it's 11.5 inches. 11.5 is a reasonable number that we can measure. 20 square root of 3 divided by 3, not something that we can just go out and measure on a measuring tape. So I know exactly what the width should be for this beam that is the strongest possible. The H squared is 400 minus 400 over 3. That's 800 over 3 in total. But that's H squared. Take the square root of both sides. H equals the square root of 800 over 3, which is 16.3 inches. Now the strongest implies a maximum strength. My second derivative is minus 6 kW, which is negative for all positive widths and constants K. Concave down, negative, tells us it's going to be a maximum. So if the width of the beam is about 11.5 inches, and the height of the beam is 16.3 inches, then this beam will have maximum strength cut out of this log of diameter 20 inches. Good to know. I am hoping this is the last one. I'm getting tired of talking here, people. Example 8. A man is in a boat 2 miles from the nearest point on the coast. He is to go to a point Q, located 3 miles down the coast and 1 mile inland. He can row a boat at 2 miles per hour and walk at 4 miles per hour. Toward what point on the coast should he row in order to reach point Q in the least time? Now, least time says I want minimum amount of time. When I'm thinking time, I know that distance equals rate times time, or distance divided by rate is equal to time. All right, let's take a look at this. On water, we'll call our distance d in blue. D is the square root of x squared plus 4, right? X squared plus 2 squared. This is our hypotenuse. And I know that he can row at 2 miles per hour. So if the distance in the water is square root of x squared plus 4, and the rate in the water is 2 miles per hour, then the time in the water, or water time, is the square root of x squared plus 4 all over 2. Do the same thing for the land. I labeled the land with my green D. So land is 3 minus x, right, according to what they have labeled on the coast, all squared, plus 1 all squared, and we'll take the square root of that. We found earlier that it's much easier to have a polynomial underneath our radical, so I simplify 3 minus x all squared, add my 1, and I have x squared minus 6x plus 9 plus 1. It gives me x squared minus 6x plus 10. And then we're going to divide that by the 4 miles per hour he could walk on land, and I have the amount of time for land. All right, so the man's on water for a while, he's on land for a while. The total time will be the time on water plus the time on land, which I can rewrite as 1/2 square root of x squared plus 4 plus 1/4 the square root of the polynomial x squared minus 6x plus 10. Now we're going to get even more technical. Make sure that makes sense before you carry on. That's when pause comes in handy. In order to minimize time, I need to take the derivative, find where it's undefined, find where it's 0, and deal with our life. Here we go. Finding the derivative of time. I leave that 1/2 alone. I use the chain rule. 1/2 parentheses x squared plus 4, close parentheses to the negative 1/2. Don't forget to multiply by the derivative of the inside. That's our 2x. Plus, leave the quarter in front. Once again, use the chain rule. 1/2 parentheses x squared minus 6x plus 10, close parentheses, to the negative 1/2. Don't forget to multiply by the derivative of the inside. The 2x minus 6, also in parentheses. When I simplify, I end up with x divided by 2 square root of x squared plus 4 plus x minus 3 over 4 square root of x squared minus 6x plus 10. Go through it. Make sure I did my cancellations correctly. Make sure I set that up right. Make sure you understand that step before you move forward. Now, I want a minimum time, so I want to set my derivative equal to 0. We'll worry about where the derivative doesn't exist in a little bit. T prime equals 0. I'm going to subtract x divided by 2 square root of x squared plus 4 from both sides. Because I have radicals in my denominator, I'm going to square both sides. This could give me extra answers, but that's all right. We'll realize our domain when we get there, hopefully. When I square both sides, I'll end up with x squared over 4 times parentheses x squared plus 4 equals x squared minus 6x plus 9 all over 16 times x squared minus 6x plus 10. Multiply both sides by 4 to simplify. Now I cross multiply, have some hideous polynomials. Some x to the 4ths going on. I simplify, reduce it down to x to the 4th minus 6x cubed plus 9x squared plus 8x minus 12 equals 0. Now, once again using methods of precalculus, section 2.6, where we talked about the rational zeros theorem and how to find these zeros. we're just pulling out a graphing calculator and looking for intercepts here. Roots, I find that x equals 1 or x equals approximately negative 1.11. Now, why would he row to the left if he was going to a point on the right? This does not seem like it would be the shortest amount of time. We could ignore that. It's a ridiculous answer. X equals 1. The other two roots, by the way, are complex roots, so they're not a part of our real solution. X equals 1. The man should row toward a point 1 mile down the coast in order to minimize his travel time to point Q. Now you know, if you're ever stuck out in the ocean, how to get there. I would encourage you to not work this out, though, and just get out of the water as soon as you can. If you have any questions, let me know as you complete this homework. Thank you.